Hello everyone. Today we'll be talking about fiber optic communications. There are different type of communications, electronic communication, satellite communication, but unlike other type of communications where we use the microwaves or the radio waves which range from lower range in kilohertz and up to gigahertz. So here the fiber optic communication is unique because the carrying capacity of this particular type of communication is infinite. So in this discussion, in this presentation, we will be talking about different things: introduction, principle of working, basic elements, types, modes and losses in optical fibers. So if we talk about optical fiber cable, it's nothing but a fiberglass make, or it can be clear plastic make, thick, which is slightly more thicker than the human hair, that can function as a waveguide. And actually in this fiber optics we talk about the science and engineering that deals with the design and application of optical fibers. And why we need these optical fibers? Because comparing to the electronic communication system where the loss is too much, plus the wavelength has a limitation. And one more thing is, which is very important, is that in the electronic communication there can be interception, and interception of signal is a big issue, especially dealing with the defense or police department. And this kind of communication which is dealing with the optical fiber, it uses the light as a signal, and therefore it is free from such interferences which can happen. And here the different type of fibers are used, which I will be talking in the later part, which are like single mode and multi mode. And this particular phenomena, this particular type of communication makes use of a very simple phenomena of physics, which is known as total internal reflection, where we require two different media and where the total internal reflection is obtained by changing the angle of incidence, and about which I will be talking later on. Then here in this particular type of fiber optic communication, we make use of the electrical signal initially, but it is converted into optical signal by means of light emitting diode or injection laser diode, because these are the devices which can convert the electrical signal into the light, which can be coupled to the fiber cable, fiber core, and which can propagate in the core to travel to longer distances. That is one component. And at the end, at the receiver side, we make use of photodiode, where the light signal is converted into corresponding electrical signal, and that can be recovered as it was in the original. And on the way it travels not through space but through cables only. So everything is, the whole signal is passing by through the core of the fiber cable. And as we know, the whole world is connected by the fiber cable everywhere, and it has infinite carrying capacity. So on the way, the lots of lakhs of kilometers, thousands of kilometers of cables are required for the propagation of the signal, for which we face the problems. One of that is the losses. Different type of losses take place in the signal, which can be reduced by using the repeaters. So depending on the loss, which is measured in decibel per kilometer, we used to put repeaters on the way. Sometimes we used to hear that due to some problem, due to bending of the cable, no internet. So those things happen because of the bending, which may happen anywhere, which may have environmental reasons. One of that may be in the Pacific Ocean, where the cables are passing through the seabed. So due to the water pressure or other reasons, if the bending is really critical, more than critical, or more than a limited diameter, then it results into the losses of the signal, or sometimes total breakdown of the signal. So all those things we can take care by using the repeaters, and also by repairing at the spot, which are done by ships, and in those situations whenever there is a breakdown. So this particular diagram gives a small idea about that, how the transmitter and receiver both are part of it. And actually when as I said earlier, the repeater, actually in the repeaters we use both transmitter and receiver. So here you can see that from in the transmitter circuit you have the light source which actually converts the electrical signal into light signal, which passes through the fiber cable and it goes to the receiver side where we have detector and we have receiver circuitry, where the light signal can be reconverted into corresponding electrical signal. The basic elements of this fiber optic communication are the light source, low loss optical fiber, photodetector and accessories. So as I told earlier, the light source, it can be light emitting diode, it can be injection laser diode. When we say low loss optical fiber, that means in the manufacturing stage we have to make it sure that the material that is developed for the optical fiber core should be the best possible control or the best quality, where the loss of the signal should not happen. Then photodetector is another part which comes in the receiver side, and this particular communication requires a lot of accessories like connectors, switches, couplers and multiplexing devices, amplifiers and splices, because it is this fiber optic communication, actually there is a physical connection of around the whole world, and that's why we call it global village. This thing has been come into the reality because of the connectivity through fiber cables, and these fiber cables are having the infinite carrying capacity of information, and that is why we all are connected, the whole world is connected, and we do not feel any time in taking any kind of action on the internet. Anything we use, whether it is audio, video, text, anything, all that happens with instantaneous time. Then some more points, that core, cladding, buffer and jacket, these are the different components of a fiber cable. And when we talk about the optical fiber cable, as we can see in our university also in different roads, there is OFC, OFC is written. That OFC mark is for optical fiber cables. And if you see the just by looking at the color of the cable, you can understand what kind of cable is this. If it is single mode cable, it is in the yellow color, and if it is orange color cable, it has multi mode. That means more than one mode of the propagation is happening inside the core. And as I told in the beginning, that the entire process of the signal propagation depends on a very basic physics phenomena which is called total internal reflection, where this makes it sure that the light goes on traveling or propagating through the core. And as I told in the beginning, the size of this optical fiber is really very thin, 0.25 to 0.5 millimeter. Something more will come in the next slide. So here, if you talk about the single mode fibers, they are used for telephone and television sets mostly, and multi-mode fibers are used to transmit lots of signals, more than one. So many signals per fiber, and this many signals per fiber, they are used in computer and also LAN, local area networks. So the optical fibers has become a part and parcel of our life in one form or another for the communication purpose. Then we come to the another side, that means the receiver side of the fiber optic communication system. Here we talk about the photodetectors, and photodetectors are nothing but these are the devices which can convert the light energy into corresponding electrical signal. And here the photodetectors which are more popular in this fiber optic communication, generally two, PN photodiode and avalanche photodiode. So depending on the application, wavelength, the material composition, so we can make use of that. Generally this kind of diodes are manufactured using silicon, germanium or indium, gallium arsenide. So these are the materials which are used for this particular type of photodiodes, and these diodes play a very crucial role in the recovery of the signal, because after the photosensitive cathode, the light generates corresponding electrons, and therefore the corresponding electrical signal is generated, which we can send to the amplification side and we can recover in the original form. Then when we talk about the total internal reflection, for this to happen, there are conditions where the light should travel from higher refractive index material to the lower refractive index material. So that is achieved here by having the cladding. The cover of the core is actually called as a cladding. So this cladding or the cover helps to achieve the total internal reflection. In what way? The core refractive index and the cladding refractive index are in such a way that N1, if we call N1 as the refractive index of the core and N2 as the cladding, so the condition is that N1 should be more than N2. And second aspect is that the angle of incidence. The angle of incidence, the light traveling from the core to the cladding, that means from higher refractive index medium to the lower RI medium, when it travels, the angle of incidence we should go on changing, and if the angle of incidence is achieving to the critical angle, that means when angle of incidence becomes equal to the critical angle, the light traveling from the higher refractive index medium to the lower medium will be refracted at 90 degree. So this is a very crucial point. Suppose we increase the angle of incidence more than critical angle. So in that situation, the light actually doesn't go outside and it comes within the glass medium. That means it reflects back into the medium from where we have tried to send to another one. That means in the core itself, it will come back to the core if the critical angle is if we increase the angle of incidence more than critical angle. Then after that, the entire light, entire signal comes back and bounce back. That is what we call total internal reflection. So this is the basic principle by which, through which the signal, the propagation takes place throughout the journey of the signal. From this picture you can see that how the single mode and multi-mode fibers are there, how they look like inside. If you can see the core and cladding both. So the core may have single mode or core may be multi-mode type capacity. So depending on the size, also depending on the manufacturing, we have both type of cores, that means both type of fibers which can handle single mode and others can handle multi-mode. So depending on the application, we can make a choice of it. Then when we talk about fiber mode, then light energy across the fiber, we call it as a mode, and the variation in refractive index create boundary conditions that shape how the light waves will travel through the fiber. Incident rays at different angles can all stably travel down the length of the fiber as long as they hit the core cladding interface. So the main thing here to understand is that fibers that carry more than one mode, actually their size is bigger, their diameter is higher, like you can see here 50 to 100 micrometer, while single mode just 8 to 10 micrometers. So in the one main difference in the two type of modes is that in the single mode, the optical signal is straight line at the that means the optical signal travels in a straight line in case of single mode, while it is different in case of the multi-mode. So from here you can see the different type of core cladding sizes, and also step index multi-mode fiber, graded index these are the different types of the fiber, and by developing the material of the core having different or variable refractive index, we can achieve this kind of things. Of course, it is the part of the manufacturer of the core. Then another issue which is very, very important is that whenever we talk about the signal, the light signal traveling into the fiber, there is always a chance of losses. So there are different type of losses which take place in the material, and those type, since our signal is in the form of light, so any type of losses to the light means loss of the signal. What we have sent, we are going to face different type of losses in the process. So as I told in the beginning that we calculate the such losses in the unit of decibel per kilometer, and therefore at different intervals we used to put repeaters. Those repeaters refresh or recharge the signal before they go to the next journey. So if I want to explain the repeater in very short way, it is like the integration of transmitter and receiver both, because we are putting the repeater which receives the light signal in a poor way. So that light signal, when it is coming in a poor intensity or poor signal, then we need to amplify that signal first, and after amplifying the signal, we when the signal becomes strong again, then we have to transmit, and therefore the repeater is nothing but receiver and transmitter. If you reverse the system, like in the general communication we say that transmitter and receiver, but in the repeater it is reverse. The signal which is poor is received by the receiver, and then it converted into electrical signal, it is amplified, and then it is again converted into the light signal. So by means of the different techniques, including the modulation. So including the modulation, optical modulation technique, we can make the poor signal into a stronger one, and we can allow that to travel to the further part of the journey. So in this fiber optic communication systems across the globe, this is a very important part, that is the repeater. Without repeater, it is very difficult to maintain good quality signal to all the users. So now we'll be talking about the different type of losses which take place in the optical fibers. That means intrinsic loss in the fiber material. Second is scattering due to micro irregularities inside the fiber. So these two losses are present intrinsically. That means these losses are not because of the environment or because of the user or because of the any other parameter, but they are these kind of losses are actually crop up during the manufacturing of the material. So when this core is developed in the industry level, so at that level this kind of problems, the first and second, are available, and that is why we call it intrinsic type of loss. So intrinsic loss in the fiber material, and then scattering due to micro irregularities inside the fiber. That means when we are manufacturing, when the industry is manufacturing the fiber core, it is very difficult to maintain its diameter, its all the properties throughout lakhs of kilometers, because the whole world is connected with fiber cables, so it is not for few kilometers. So it is a big challenge, and therefore whenever we develop, whatever precaution we take, there is always some problems, some irregularities inside the fiber, or intrinsic losses, they are always present. So that's why the first and second loss, we call it as intrinsically present, and the other two, that means micro bending losses due to micro deformation of the fiber, then the bending or radiation loss on the fiber. So if we look at the third one, micro bending losses due to micro deformation of the fiber. So as I told that this kind of system, this kind of cables, we have to take each and every place, everywhere across the globe. So everywhere the kind of topography, the kind of situation is there is not the same. So sometimes you need to bend it before you are putting it under the maybe seabed or under the earth, inside the earth. You are digging and putting inside. So it is very difficult to maintain that everywhere it will be straight line only. So bending is naturally, it has to happen. So if bending is not too much, we call it micro bending, and this bending happens with the core or with the cables because of the micro deformation of the fiber. So in the micro deformation, there is no big loss, but still there is a loss. Now if this micro deformation actually exceeds a limit, like the last one, that is bending or radiation losses on the fiber, as I told in the beginning, that sometimes we face a sudden breakdown in the internet, and then we come to know sometimes that this problem is crop up in the Pacific Ocean, then sometimes many other places also. So like why Pacific Ocean comes into picture, because the cables, the fiber optic cables are there in the seabeds, because they are connecting from one continent to another continent, like that. So it can follow this kind of cables. They have no defined way. They follow, they can be put in the water also, they can be put in the soil also. So wherever it is required, we have to put it. We cannot follow a hard and fast rule, because this connectivity has to reach to everyone, be it very remote, be it very advanced place. So that is why the bending of the cables is natural to happen. But when this bending becomes too much, suppose in the seabed, because of the water pressure, huge depth and water pressure, the bending becomes too much, then what happens, that the signal movement, it goes more or less blocked, because due to bending, the movement of the light is not within the limit, which we can say that, like, sometimes there is a slow internet. So this is because of the bending, which is kind of category of the micro deformation bending. But when it is exceeding the limit, the losses becomes too high, and therefore sometimes either we get a very, very poor internet, or sometimes no internet. So this type of problem, the number 4, 3rd and 4, these are not responsible, or these are not coming from the manufacturer, but they come from the environment in which we are laying down the fiber cable. Then there is material loss, as I told in the beginning, that this loss is carried with the material, by the material during the manufacturing process. This is not because of the user or because of the environment. So here impurities which can be present here are iron, nickel, cobalt, aluminum. So this type of losses, they get reduced beyond 1200 nanometer wavelength. So within 1200 nanometer wavelength, such kind of losses are high. So that means the losses will not be everywhere same. It depends on what range of wavelength you are using. If you are using below 1200 nanometer, the losses will be high. If it is more than that, they will be reduced. Now another reason for the material loss is due to OH molecule. Like whenever we are those people who are working in the industry, we are talking to each other, and therefore even the micro, even very, very small molecules of water or vapor may be coming in the process, and therefore they may create problem in the material. In what way? The OH molecule diffuses in the material and causes absorption of light. So that kind of even tiny spot which is generated because of the OH molecule will create problem in the form of absorption of the light. That means we are losing the signal. Then here the main absorption peak in deep infrared region wavelength, showing substantial loss in the range of 1000 to 2000 nanometers. So here also the loss is depending on the range of wavelength that we are making use. Then due to infrared absorption. So glass intrinsically is a good infrared absorber, we know that, and as we increase the wavelength, the infrared loss increases rapidly. That means as far as the loss due to infrared absorption in the material is concerned, if we use the wavelength which is in the higher side, the larger range, then in that case infrared losses can increase rapidly. That means for infrared absorption side, it is better if our wavelength range is not too high. Then another type of loss, which is scattering loss, which is also from the material side. This is due to non-uniformity of the refractive index inside the core of the fiber. As I told in the beginning, that to achieve the total internal reflection, the refractive index of the core should be uniform throughout, everywhere, across the globe, wherever we are using. But it is not always possible to have exactly or uniform refractive index throughout the core fiber, and therefore this fluctuation happens, and therefore refractive index of an optical fiber has fluctuations of the order of 10 power minus 4 over spatial scales, which is much less than optical wavelength. And therefore what happens? The scattering loss varies as wavelength, that means lambda to the power minus 4. This way it varies. So this loss rapidly reduces as the wavelength increases. So here also, if we are making use of the higher wavelength, then losses will be reduced. For each doubling of the wavelength, the scattering loss reduces by a factor of 16. That means if you are increasing the wavelength 2 times, then loss will go to a factor of 16. So that is one way of handling this kind of loss. Now radiation and bending loss. When we say the radiation and bending loss, as I told in the beginning, that the kind of bends that are generated when we are laying down the cables in different type of environment. So depending on the topography, depending on many other things, the kind of bend which is there, it may be micro, it may be slow bend. So we categorize in the two way. One is micro bend, another is slow bend. So micro bend is on the micron scale and slow bend is on the centimeter scale. So like if we talk about as example, a typical example of a slow bend is the formation of optical fiber loop. So if this kind of loop formation is there, then this is categorized as a slow bend where the loss is higher than that of the micro bend. The light inside the fiber propagates in the form of modes, and therefore the modal fields decay inside the cladding away from the core cladding interface. That means because of the interface between the core and the cladding, there is likely of modal propagation or losses due to this can happen. Then bending loss. Bending loss, when we say it, as I told in the beginning, that bending, when we say, it has lots of ranges. That means when you are using the cable, when you are laying down the cable, it may be very simple path. You don't have to bend. Somewhere you may have to bend a little bit. So these different ranges of bending are there, and therefore the losses also depend on the extent of bending, the degree of the bending of the cable. So it will go like that, and therefore when we are laying down the cable, the people who are involved should be trained so that the loss is reduced as much as possible. And for that, actually in the cable itself they used to write that up to what diameter your bending is okay, is safe, or will not have drastic problems. Then for this particular bending loss, I would like to say few more things, that this kind of loss of the bending which is happening by different ways and means. So as far as possible, we should avoid using or laying down the cable which is going to a very sharp bend. We should not put our cable there, or we should avoid our cable putting where there is lots of activity of digging, etc. Otherwise, what will happen that during the process of digging or agriculture practice or anything else, it will happen that the cable may be cut down by somebody. So that's why these precautions as far as possible should be taken, of course, keeping in view of that also, but we have to connect to everyone, so that is also important thing. So everyone, that this kind of connectivity should reach to everyone, that is another issue. So in total, or as a summary if I tell you, then this particular type of fiber optic communication today is the backbone of the global communication. We are connected to everyone, everywhere, because of the fiber optic communication system. And as I told in the beginning, it has lots of merits over the traditional electronic communication system, where one of the biggest problem was the wavelength. You want to transmit more information, your transmitter size should be increased, and many other input parameters you have to change, and the investment in the sector, in that particular communication system, sector, you have to increase. And not only that, when the microwaves travel through space, different type of losses, and as I told in the beginning, interception is one of the issue, which doesn't happen here in this particular type of communication, because we are using light as a propagation mode, and light cannot be intercepted by using just electronic receiver or whatever receivers we have of today. So it cannot be used. So it gives us a communication with protection, with no other type of losses, and also heating loss also is reduced. So when I say fiber optic communication, it doesn't mean that it's standalone, but it is an integration of electronic communication and optical communication. So integrated approach of both actually gives us this wonderful type of communication system, which we call as fiber optic communication. And this fiber optic communication system actually is taking care of everything, and we can do this in most advanced systems or old systems, 1, 2G, 3G, 4G, 5G, whatever we want, everything is available and everything is working under this. So with that, I conclude, and these are the references that have been used in this particular discussion, and thank you very much for your kind attention.